Hi, everyone. Hi, I'm Maple. Today we'll be looking into peephole optimizations. But before we start, I want to share something. So I recently quit my job. And so I've come to learn the importance of having a community. And so I'm actually here today with you because I'm sponsored by WMB2RB. I know Gemma has already said something about this, but I just wanted to share that this community has been really helpful to me. So if you are a woman or a non-binary folk, please join us, and we'll be meeting right after this talk at Espresso House Hakanemi. So I hope to see you there. It'll be really fun. All right. So looking into peephole optimizations. So peephole optimization is an established technique that was written about back in the 60s. And that was a really long time ago. So this is the earliest paper I could find on the topic. So I think it's really, really interesting to learn such an established optimization like that, because it helps us understand how the system works overall, and it builds our foundational knowledge to future compiler optimizations. So if you have compiler experience, I hope this talk will refresh your memory on the topic, and you'll also learn something new about how Ruby does peephole optimization specifically. And if you're a total beginner, then I am you. I've written this talk just for you. I hope you will feel like you learn more about how how Ruby is compiled, and also how specifically this optimization works. So what to expect from this talk? First, we're going to talk about, obviously, what is peephole optimization. We're also going to talk about when does peephole optimization happen in Ruby, and how Ruby implements peephole optimization. And we're going to go into examples of peephole optimizations in Ruby. And in doing so, we're going to learn about some yarv instructions. So yarv is a Ruby VM. It's called yet another Ruby VM. And then we'll talk about some of how the bytecode works and all that. It'll be really fun. And then finally, we'll end with big picture and benchmarks. So what exactly is peephole optimization? So it involves looking at a small set of code, usually intermediary instructions or bytecode, to find and change the instructions to be more performant in some way. And so the resulting instructions are usually less redundant and less complex. So how does it get its name? So the reason why it's called peephole is because it looks at several instructions at once. I don't really know why it's... because in a peephole, you can only see what's directly in front of you, I guess. But peephole nowadays, you can kind of see the whole view. So I don't know why it's named that. So this optimization can be applied to various other languages and machines. So for example, peephole optimization is also used in languages like Python. It can also be used to optimize assembly code, and YJIT also uses it to optimize their bytecode. But today, we'll be talking about it in the context of Ruby, so MRI. And this is just a paper I found. So peephole optimizations could also be used to optimize quantum compilers, which is really cool. So another note is that Ruby currently implements peephole optimization already. So you use it in your Ruby code. It's turned on by default. All right. So when does peephole optimization happen in Ruby? So this is a graph of essentially the entire Ruby execution process. So it starts from your Ruby code, which gets passed into a tokenizer, which produces tokens. That gets passed into a parser, which produces AST nodes, to the compiler, which produces bytecode. And that bytecode gets executed by the virtual machine. So the phase that we're talking about in this talk would be the compiler and bytecode phase, where the compiler generates bytecode. So let's zoom in a little into this specific phase. And let's use this as an example. Essentially, we have a puts 9 plus 8 string into the variable source code. And you can kind of ignore this graph on the left. It's essentially what the puts 9 plus 8 source code is represented in AST nodes, and that gets passed into the compiler. But let's take a look at what the bytecode looks like. So in order to do that, we use this library called the Ruby VM instruction sequence library. And what we want to do is we use the method called compile that takes in the source code. And then we want to disassemble it, because when the Ruby code is compiled, it's not readable. And then when we disassemble it, it is human readable. Next, this is the output. So don't get overwhelmed. I just want to show you kind of what it looks like. But the main thing to focus on is essentially this little chunk, which is the bytecode instructions, or the YARV instructions. And so we can conclude now that this is the output. Oops. This is the output of the compiler. It's kind of simplified. It's essentially the same as what the code output in the previous slide. All right. So another thing that you have to know is that when the compiler outputs this bytecode, it's actually arranged in a linked list structure before it is passed on to the Ruby VM. So just pulling back now to how this relates to Peephole optimization, when the compiler generates the bytecode, it is then optimized into more optimized bytecode before it is actually passed to the virtual machine to be executed. So that brings us into the next part, which is how does Ruby implement Peephole optimization? And to avoid showing you a bunch of C code, I have kind of wrote this pseudocode of iseek optimize. So iseek optimize is a function in compile.c in the Ruby implementation. So let's kind of walk through it. The first thing it does is set up some optimization options, obviously, because it's C, so we have to set up some stuff. And then we iterate over the linked list, so in a while loop. So for each element, we do this. Next, we check if the element is an instruction sequence. So there are different elements, which we won't go into here, but what we care about is an instruction sequence. So if it is an instruction sequence, and if Peephole optimization is turned on, which we know is turned on by default, but you can change it, obviously, we want to call the function iseek peephole optimize. After that, there are various other optimizations, which we won't go into in this talk. And then we move on to the next element, because it is a linked list. OK, so just to quickly show you visually, what it does is that it essentially traverses the linked list. All right. So now the question is, what happens in iseek peephole optimize, which is the C function that we call within that if condition? It's very long. It's very long, but I highly recommend checking it out after this talk if you're curious to what other Peephole optimization cases there are, because it's pretty well documented. You can see it, but it's for each case, it is there's a comment on what the before and after is of the bytecode. But anyway, moving on. It's a bunch of if conditions, but I kind of simplified it for you a little bit here in this pseudocode. Essentially, for each element that we're checking, we want to see if it matches any of the cases of the optimizers. So before you say anything, yes, it's basically like a pattern matching function. It's like pattern matching and then conditional replacement if it matches that case. And just a fun fact, I actually did a survey of the entire function, and there's actually like 20 to 30 cases of Peephole optimization cases out there, so that's pretty cool. And also, if you're curious, there's actually a paper out there that implements Peephole optimization in a pattern matching kind of sequence. So if you are interested in pattern matching, you should check this out. All right. To recap, iseek optimize, so the first C function that I showed you, essentially traverses each element, and then we call iseek peephole optimize to check. So this is what happens. So when it reaches an instruction that is the optimization case, what we do is ask whether it matches, and if it matches, we replace it to a more efficient instruction. And then we move on. So essentially, that's how Ruby implements peephole optimization. So after the peephole optimization pass, the instruction sequences should be smaller in size and also more performant. And you'll kind of see what I mean in just a second. So next part is, I think, the more interesting parts, which is examples of peephole optimizations in Ruby. So the first example I'm going to show you is combining multiple instructions into one single instruction. And the source code will be this. So if you didn't know, this is essentially a range from A to Z. And the double full stop is to indicate that it's inclusive. So for example, you can call count on it, and it will return 26, because there are 26 alphabets. And you can also call 2a on it, which gives you an array of letters. So what we want to do is very similar to the first bunch of code that I showed you, except in this case, we're going to turn peephole optimization off. And let's take a look at what the output for this is. So similar to before, this is the the bytecode output, but I've simplified it for you. So essentially, it is put string A, put string Z, new range with the argument 0, and we'll see what that means in just a second, and then we leave, which is the equivalent of returning. So the first instruction is put string A. Put string A essentially pushes a string literal onto the stack. And put string A pushes A, put string Z pushes Z. And the next one is new range with the argument 0. And new range creates a range, and it takes one argument, which is 0 if the n is included, or 1 if the n is excluded. So we know that it's 0 because, as I mentioned before, it's 2 full stops, and so it's inclusive. So let's take a look at how the Ruby VM executes these instructions. So if you didn't know, the Ruby VM uses an internal stack to manage values. So you'll see how it works in just a second. So let's go through the instructions. So put string A pushes A, put string Z pushes Z, and then we call new range, which pops 2 elements off the stack and pushes a range, A to Z, back onto the stack. That is inclusive because the argument is 0. And then we leave. So I want you to make note of what value is on the stack right now. OK, let's take a breath. Next, we're going to see how Ruby optimizes it. So with peephole optimization turned on, this is the output. It's just 2 instructions. And we have put object A to Z. So put object essentially pushes a known value onto the stack. So you can kind of see where this is going. Basically, this. You just push the range. And it returns the same value. And this is the diff. So instead of having 3 instructions do the same thing, we just have put object with the range that you want. So I ran a micro benchmark on this, and it's actually 5.4 times faster. So that's really cool. OK, so moving on to the next example. Removing unnecessary instructions. So this is a very contrived example, but essentially, it is hello world in an array that is splatted. And if you didn't know, this kind of returns an array of just hello world when it's run. So doing the same thing, we want to turn off peephole optimization and see what it returns. So OK, this is the simplified version. We already know what putString does, so let's skip that. There's a new instruction here called new array, which takes in the argument 2. And new array puts a new array initialized with the size value from the stack. So what that means is that it pops the stack however many times it is specified in the argument, creates a new array, and pushes it back onto the stack. And another new instruction here is splat array. So splat array essentially calls to on an array to splat it. So the reason why we have splat array is because we can't assume that whatever is on the stack is an array. And so split array exists to make sure that we're actually executing an array. All right, so let's take a look at how the Ruby VM or Yarv would execute these instructions. Put string hello pushes hello, push string world pushes world, and then we call new array 2, which pops 2 elements off the stack and pushes a new array with the 2 elements. And then we call splat array, which pops something off the stack, calls 2a on it, and then pushes it back onto the stack, and then we leave. So I want you to take a second to see if you notice any redundancies. And then let's take a look at how Ruby would optimize this with Peephole optimization turned on. And this is the output. And essentially, you can see that we actually don't have splat array anymore. And the reason is because we don't need splat array, because we know that new array 2 always returns an array onto the stack, and so we can save on one instruction. So I did a micro benchmark on this. It is 1.31 times faster. All right, so to the next example. Removing redundant instructions. It's kind of similar to removing unnecessary instructions, but anyway. So this is the example code. So we have gummies are the best, which they are in the string, and then we assign it to x. And then for some reason, we want to assign x to x again. So yesterday, while I was preparing this talk, I showed this to Jean, who most of you will know as byroot. And I'm like, who's ever going to do x equals x? Turns out he just wrote this code last week, which is essentially x equals x, because I checked. And this is actually a Rails PR. So this code is in Rails. And I checked because the Peephole optimization is actually works on this Ruby source code. So that's pretty cool. OK, anyway, moving on. What we want to do is turn off Peephole optimization. This is the output, and this is the simplified output. So there are a couple of new instructions here. So the first one is set local with index 0, and set local essentially sets the value of the local variable on a frame. And the reason why previously you'll see that it's index 0 is because we only have one local variable, which is x. And so we set it to x. And then the next one is get local. And similarly, it fetches the value of the local variable from a frame. And the third new instruction here is dupe. So dupe copies the top value of the stack and pushes it onto the stack. But in this case, the dupe instruction just duplicates the pointer reference of the top object on the stack. It doesn't actually make a copy of that object. So let's take a look at how Ruby VM would execute these instructions. Put string, we know, push string onto the stack. And then set local at index 0. We pop the first object off the stack and set it. Just a note here, this is just for visualization purposes, but in reality, Ruby actually manages local variables a little differently. There's a separate local table here just for you to understand it. But anyway, so we set x to be gummies are the best. And then we get local, which looks up in the local table what x is, and then push that onto the stack. And then we dupe it. And then we set local again. But it's already set. So you can kind of see where I'm going with this. And then we leave. So with Peephole optimization turned on, this is the output. And yeah, wait. So this is the instruction. So let's take a look at how the Ruby VM would execute it. And you can pretty much see where I'm going with this. So we push gummies are the best onto the stack, set the local variable, and then get the local variable, which is the x equals x part of the Ruby source code. And then we leave. So this is the difference in the optimization versus no optimization. And let's take a look at the benchmarks for this. Surprisingly, or maybe not so surprisingly, there is no difference. It's not slower. It's kind of marginally faster. But there's no huge difference in CPU performance. But this kind of makes sense because, as I've alluded to just now, when I was talking about dupe does not cost a lot to execute because it's just a pointer duplication and not a copy of an object. So this is an example of kind of a clean-up optimization where it makes the code less complex. And in turn, does save us on instruction sequence memory size. All right, so moving on to the last example, it is using more efficient instructions. So the example code for this is an array containing 1 and 2, which is assigned to the variable foo, and then we split foo in an array with 3. OK, so you know the drill. We turn off optimization, and this is the output. This is the simplified version. We can see that dupe array is not something we've seen before. Let's take a look. Dupe array copies a literal array and pushes it onto the stack. And concat array, so we kind of know what set local is, get local is, split array, I've talked about it before, and then dupe array. But now we have concat array. And concat array pops 2 objects off the stack and concatenate them, and then pushes it back onto the stack. So let's take a quick look at visually how it happens. So dupe array pushes 1 and 2 onto the stack. Set local sets it to the local table, and then get local gets it. Split array pops it off the stack, pushes back on. Sorry, I know I'm essentially narrating what's going on, and you can obviously see it. And dupe array pushes 3 onto the stack, and then concat array pops 2 objects off the stack, concatenates it, and pushes it back onto the stack, and then we leave. All right. So with Peephole optimization turned on, this is the output. It's not very obvious what changed because it is the same amount of instructions. But here's the diff. Essentially, we swap out dupe array 3 for put object 3. And the reason is because dupe array allocates a new array while put object does not. So this optimization actually runs 1.26 times faster. So those are the examples that I have. Let's talk about the limitations of Peephole optimization. As you can already, as you probably have noticed, this optimization kind of only applies to very specific bytecode. We're not all Jean writing x equals x all the time because it's literally an edge case. So it kind of may not apply sometimes when we write day-to-day Ruby code. Next, Peephole optimization Peephole optimization only has a limited view into the code to make optimization decisions. And a couple of talks already have mentioned this, but Ruby is a dynamic language, so it's very hard to get information at compile time. So for example, Ruby methods can be monkey patched. So we won't know until runtime which method we're actually going to be calling. We also can't do stuff like get rid of unused local variables because some of them potentially need to stick around if binding is called. And some optimizations that are common to statically typed languages, such as algebraic simplification or expression rearrangement, is also really hard to do with Ruby for that reason. And finally, Ruby does not yet inline methods, so people could potentially work more effectively with method inlining in Ruby, which hopefully we will get in the future. So one question that you might be wondering while listening to me up here right now is that why doesn't the compiler just generate optimized bytecode? Like, why do we need to have this optimization pass? And the reason is because of the way that the compiler is implemented. It is unable to see the bigger picture, because essentially what it does is translate the AST nodes into bytecode. And so it kind of makes sense to split up the responsibilities of the compilation and optimization process. All right. So another limitation is that, at least in Ruby, these optimizations have to be found and written by humans. And what that means is that it's not super optimized. There might be better optimizations out there, but we won't know until we find out. And there is Peephole super optimizers out there, but it's just not implemented in Ruby. All right, so I'm going to share with you some benchmarks. Using an established benchmarking library called YJitBench, you've probably heard of it. I ran benchmarks that measures I ran benchmarks with both the Peephole optimization turn on and the Peephole optimization turn off. So essentially, it shows some modest improvements with the Peephole optimization turn on, which you can see in the last column over there. All right, so one thing to note is that on top of the performance improvements, which I just showed, there's also a reduction in instructions emitted. So in turn, also the reduction of the total memory space used. So it's not just CPU improvements, it's also a reduction in memory space. All right, so essentially, this is towards the end of the talk. I wanted to share with you this YARV documentation that was written by Kevin Newton. If you're interested in checking out what the bytecode instructions do, please check out this library. It's really good. It essentially implements YARV in Ruby, which makes it easier for all of us to understand, I'm sure. And then another thing that I wanted to share is this PR by John from GitHub. I mentioned before that Peephole optimizations are found and implemented by humans. So it's essentially what he did in this PR, which that he noticed that there was a case that could be improved. And it is the example that I showed you where he swapped out dupe array for a more efficient instruction put object. And so hopefully you feel like you kind of know what to look for if you're ever interested in diving into this. I haven't really told you how to potentially write your own Peephole optimization, but I think you have the tools. And these are the links to the two resources that I shared. And that is all. Thank you so much for listening. It's an honor to be here.